All right, welcome Semester 2 Engineering recruits. So glad you're joining me. Today, we're going to dive into the absolute foundational concepts of structural analysis. Think of this explainer as your conceptual roadmap. Because look, before we get completely lost in the heavy calculations coming up in your classes, we really need to understand the basic anatomy of a structure. We need to know how to take a physical, real-world beam and map it perfectly onto a piece of paper.
So I want to start off by asking you a pretty critical question. Why do some structures stand tall for literally centuries, while others fail catastrophically? The answer isn't magic, right? Actually, it's just pure physics. It's all about knowing exactly how a structure responds to the forces that are actively trying to tear it down. And as lead engineers, it is our job to deeply understand that response before we even think about touching a calculator.
Okay, so here's our roadmap for the day. We're going to look at translation versus rotation, mastering supports, knowing your beams, dealing with loads, and finally, drawing free body diagrams. We're keeping it strictly conceptual first, just to really build your intuition before you tackle those heavy numericals later this semester.
Let's jump right in. Section 1, Translation versus Rotation, the Physics of Movement.
At the end of the day, keeping a structure standing really just comes down to managing how it naturally wants to move when it's pushed or pulled. I want you to physically imagine pushing a beam across your desk. That's sliding motion. That's translation. It's moving an object in a straight line. Now imagine trying to twist or spin that same beam around a pivot point. That is rotation. Every single support we design in civil engineering is about stopping one or both of these specific movements.
Which brings us to Section 2, Mastering Support Types, the Joints.
You can think of supports as the actual joints of our structural anatomy. They connect the members to their surroundings, and they exert reactive forces to keep everything in its proper place. Take a look at this roller support. Notice how it restricts translation of the body along one direction only, straight up, perpendicular to the surface. But rotation? Totally allowed. Imagine a person standing on roller skates. They can't push straight down into the solid ground, but they can easily roll forward, and they can tilt or lean forward and backward.
Next up, we have hinged or pinned supports. Notice on the right side of the diagram how we resolve its reactions into two components, an X and a Y. This is super helpful because it perfectly shows how a hinge stops all sliding. It restricts translation in both horizontal and vertical directions. However, just like a standard door hinge in your house, rotation is still absolutely possible. It can still pivot.
And this leads us to a massively important definition, the restraint moment. This is an internal moment developed by fixed supports to strictly prevent the rotation of the body. You absolutely have to understand this. Without this internal restraint moment physically designed into the joint, a fixed structure subjected to an off-center load would just spin like a pinwheel and completely collapse.
And here is exactly what that looks like on paper. See those curved arrows labeled M? That is your restraint moment in action. Fixed supports restrict both translation and rotation. By combining that directional restriction with that powerful restraint moment, the joint is locked down completely tight. No sliding, no spinning, nothing.
All right, Section 3, Knowing Your Beams, the Bones.
So we've looked at the joints. Now let's map the bones. These are the horizontal members that connect the joints and take the actual physical loads. Let's take these dry textbook definitions and bring them into reality. A simply supported beam rests on simple supports. Think of a loose wooden plank just placed across a small creek. A cantilever beam is rigidly fixed at one end and totally free at the other. It's exactly like a diving board. An overhanging beam sits on supports but extends slightly beyond them, kind of like a protruding balcony on an apartment. And a continuous beam rests on 3 or more supports, very much like a long highway overpass. Honestly, connecting these terms to real-world analogies is going to make them instantly relatable when you're sitting in your exams.
Visually, here's how those setups look. Over on the left is our cantilever beam, our diving board, which is rigidly fixed at wall A. On the right is the overhanging beam, our balcony, securely supported at points A and B, but extending freely out into the air to point C. You really need to recognize these schematics instantly when you see them on your tests.
And here is our continuous beam. It consists of 3 or more supports, labeled here as A, B, and C. Remember that highway overpass analogy. When you see this multi-support setup on an exam paper, you instantly know the loads are being distributed across a much longer, continuously supported span, which means it requires multiple reactions.
Moving on to Section 4, Dealing with Structural Loads, the Stressors.
Okay, so we have our joints firmly placed and our bones identified. But what external forces are actually out there trying to break them? Let's start with the simplest load type, the concentrated load. Notice how a concentrated load is focused at a single, highly specific point on the beam. Think of it like a very heavy, dense piece of machinery sitting directly in the middle of a factory floor. All of that massive force is pressing down on one exact spot.
But what happens if the weight isn't cleanly concentrated in one place? This is a uniformly distributed load, or a UDL. It's distributed uniformly along the entire length of the beam. Imagine a thick, perfectly even layer of heavy snow sitting entirely across a flat roof. It's not just one heavy point. It's, say, 20 kilonewtons, pushing down evenly on every single meter of that 3-meter span.
Now, for our paper analysis, working with a UDL can be, well, mathematically pretty tedious. So we almost always convert it into a single point load. Here is the step-by-step trick to do that. First, identify the uniform load magnitude. In our snow example, let's say it's 20 kilonewtons per meter. Second, identify the span length. We'll say 3 meters. Third, simply multiply them to find the total point load magnitude, which gives us 60 kilonewtons. And finally, place this newly calculated point load exactly at the dead center of the span. Doing this makes your math incredibly clean later on.
We also have the uniformly varying load, or UVL. Visually, this looks like a right triangle. The math changes just a little bit here. Notice the formula on the right. To find the magnitude of the equivalent point load, you just calculate the area of the triangle. 1/2 times base times height. Simple enough, right? But where do you place it? You put it right at the center of gravity of the triangle, which mathematically works out to be exactly 1/3 of the way from the heaviest, tallest end.
Almost there. Section 5, Drawing Free Body Diagrams, Reality to Paper.
This is the climax of our conceptual roadmap, where we synthesize every single thing we've learned so far into one clear, actionable diagram. I want to read you this foundational quote straight from our source material. The structural members exert forces on supports known as action. Similarly, the supports exert forces on structural members known as reaction. Drawing a free body diagram is really just about capturing this exact continuous conversation. You are meticulously mapping the actions of the stressors against the reactions of the joints.
And that brings us to this incredibly intimidating sounding title that you'll see in your textbooks, Equilibrium of Coplanar Non-Concurrent Force System. Okay, please don't let the big academic words scare you off. This is quite simply the core principle of keeping structures perfectly balanced. Coplanar literally just means all the forces are operating on the same 2D flat page. And equilibrium just means all those actions and reactions cancel each other out perfectly so the building doesn't fall down. That's it.
Now, as your mentor, I really want you to burn these steps into your memory for solving equilibrium problems. Step 1. Identify all active forces and convert any of those tricky distributed loads into simple point loads, just like we practiced. Step 2. Determine the unknown support reactions acting on the beam based entirely on your joint types. Remember, ask yourself, does it restrict translation? Does it restrict rotation? And step 3. Apply the 3 basic conditions of equilibrium to calculate those unknown reactions. If you follow this highly disciplined procedure, I promise you will draw perfect free body diagrams every single time.
Let's do a quick recap of the anatomy before we wrap things up. To be a successful civil engineer, you absolutely must conceptually manage translation and rotation. You must correctly identify your joint. Is it a roller, a hinge, or is it completely fixed? You must know your bone. Are you dealing with a cantilever or maybe a continuous beam? You need to neatly convert your stressors, turning those UDLs and UVLs into clean point loads. And finally, map it all out visually to find mathematical equilibrium. Boom, you now have the full conceptual roadmap perfectly mapped out.
Which leaves me with just one final question for you guys. Now that you can confidently conceptualize these physical forces and perfectly draw out the maps on paper, are you truly ready to calculate the exact numbers in your next class? Because that is exactly where you're heading next. Keep this roadmap fresh in your mind, and you are going to do absolutely fantastic. Thanks so much for joining me on this explainer, and keep learning.